Hello. No, it is April Fool's. All right, so welcome to day 2 of this little experiment. Where's the cat? Cat's sleeping. All right, so today we're going to start going over L'Hopital's rule. So this is really the first new material we've done since the break, since our long break. So this will give us basically a new way to evaluate limits. All right, so this sheet is posted in this sheet's posted in Blackboard, where you go to like items by instructor under my name. I've also posted solutions to the last sheet. Okay, so I'm still going to be using this like the sheet on here, even though the writing's not that great for now, until I can find a way to hook up maybe another monitor to this thing, so that I can share my screen and still see the chat. There is audio. You might need, well, you can't hear me, so. So you might need to reconnect. If you, yeah, refresh. Mm-hmm. Yeah, you might need to enable your mic as well. Okay, so we're going to look at this new thing called L'Hopital's rule, which will allow us to evaluate certain limits which we may not have been able to do before. To start off with, we're going to review a couple questions that we do know how to do, and then we're going to redo them using L'Hopital's rule. All right, so for this first question, let's see. Looking at this first question, if I just try to plug in 4, you'll find out that you get 0 over 0. All right, if I just plug 4 in, you'll get 0 over 0. All right, so this is, I mean, this is really like one of the first types of problems that we looked at, where you had a rational function and you get 0 over 0. And we saw that this generally meant that they have a common factor. All right, so we did this, yeah, it is being recorded. So we did this by just factorating the numerator and denominator, all right, and canceling out the sort of offending term. That should say limit. The limit as x goes to 4. And then we try to factor the numerator and denominator. All right. So can anyone tell me what the numerator factors as? No, not, don't take the derivative. What does it factor as? Yeah, x minus 4 times x minus 3. Okay, great. What about the denominator? Yeah, slowly roll. Good. That's right. The denominator is the difference of squares. X squared is, of course, a square, and so is 16. So it factors as x minus 4, x plus 4. All right. So the x minus 4 terms cancel out, and those are sort of the problematic terms. Like when I plug 4 into that, that's where the zeros come from. All right. So these cancel out. And then we're just left with the limit as x approaches 4 of x minus 3 over x plus 4. And now we could just plug 4 in. So if you just plug 4 in, you get, right, 1/8. You get 4 minus 3, or you get 1 over 8. Okay, the solutions that I post will look much nicer than this. I don't know why this app is so bad at reading the pen. So it goes. All right. The next question, the limit is x goes to 0 of sine x over x. So this also looks like 0 over 0 if I just plug 0 in, right? Because sine of 0 is 0. For the answer is 1 for part B. That's correct. Yes, for part B, the answer is 1, right? This was sort of the basis of our small angle approximation for sine. So we're kind of taking this by definition, and we saw this by just looking at the graph. So I can use a different app where the writing's better, but I have to share my screen, and then I cannot see the chat. All right, so I can't answer any questions. So it's a bit of a work in progress. All right, so part B, the answer is 1. And this was, we sort of did this originally just by looking at the graph. Let me try something here. All right, so now we're gonna try a new way to evaluate these limits that use derivatives, right? So both of these looked like 0 over 0. All right, so when you're taking the limit of a quotient and the numerator and denominator both go to 0, or they both go to some infinity, either plus or minus. If I use my phone for the chat. Yeah, I could try to do something like that. I was trying to just log in twice, but it wouldn't let me. It was like saying that I'm already in the room once, so it wouldn't let me get in the room twice. All right. We'll figure it out. No worries. All right. So in both of these cases, the limit went to 0 over 0. So that's an example of an indeterminate form. Okay. And so is infinity over infinity, either plus or minus. All right. But there's a theorem basically, or a rule that will allow us to evaluate certain limits like this. Okay. So it's called L'Hopital's rule, named after some rich French guy who paid someone to do this and then took all the credit, is my understanding. So may he be an inspiration to you all. So suppose the theorem is stated, suppose that we have f and g are differentiable on an open interval containing a, where you're taking the limit, and the derivative of g is not 0 on that interval. All right. Otherwise, yeah, calc fill in. All right. If both f and g approach 0, then L'Hopital's rule basically says that that we can take the derivative of the top and bottom. All right. So this is sort of the statement of L'Hopital's rule. Rather than evaluating the quotient or the limit at the quotient, I can take the derivative of the top and the derivative of the bottom, and then evaluate it from there. All right. So note that this is not the quotient rule. Okay. So you take the derivative of the top and bottom individually, like maybe like you thought the quotient rule should have been. Okay. So if you evaluate a limit and you get one of these indeterminate forms, then we can use L'Hopital's rule. All right. So we'll do that below, basically on the two examples that we just did. All right. Let's see. All right, so I'll do the first one, and then I'll try to break you into groups and see how it works from there. All right, so if you plug in 0, this looks like 0 over 0, so we can use L'Hopital's rule. All right, and this says that we can take the derivative of the top and bottom. All right. So what's the derivative of x squared minus 7x plus 12? 2x minus 7, good. And 2x for the bottom. Oof. Thank you. All right. And now we can just plug in 4 again. So now when you plug in 4, on the top you'll get 8 minus 7, which is 1. And on the bottom, if you plug in 4, you'll get 2 times 4, which is 8. Okay, and note that this is the same as the answer we got before. Magic. Wow. Okay, so so why don't y'all try this second one out. So let me try this breaking out groups thing just as um, an experiment. So I'm going to try to break out into groups, and then maybe I can enable mics, and you can talk amongst yourselves. We're not here to judge Mr. L'Hopital. Okay, so Howard and Shreya, y'all are moderators along with me, so y'all can kind of like join the rooms, like go in and out of the rooms to try to answer some questions if they have it. We'll see how this works. Let me enable mics.
Yo,
Yo,
yo.
yo.
Okay, yes, indeed. Welcome back. All right. Um, so, please mute your mics. Yeah, I know. The uh this worksheet is posted on Blackboard under, if you go to like the materials by instructor and go to my name, it is posted on Blackboard. Okay, so let's look at this now. So the limit as x approaches 0 of sine x over x, the answer is indeed 1, as we saw before. Yeah, you're stealing my punchline. So this goes to 0 over 0 because sine of 0 is 0. So we can use L'Hopital's rule then, where we can take the derivative of the top and bottom individually, right? So then we get the limit as x approaches 0. And then what's the derivative of sine x? Cosine x. Okay, so x has got it. Cosine x. BT dubs, indeed. All right, and then the derivative of x is just 1. So if you can't see the writing, I think you probably just need to reconnect. Yes, Gabriel. Dost thou have a question? Okay, so now we can plug 0 in basically. I'm not dividing by 0 anymore, right? So if I plug 0 in, cosine of 0 is just 1. So you do indeed just get cosine of 0, which is 1. Okay, any questions on that before we move on? So we're basically just going to do some more examples. No comment. No comment. Well, we didn't know derivatives first, so there's a bit of a prerequisite involved. Okay, so now let's look at these. So some of these you'll use L'Hopital's rule and some you won't. So one thing to keep in mind is that you can only use L'Hopital's rule if you're able to write your expression as 0 over 0 or plus or minus infinity over plus or minus infinity. Okay. So let's look at A. All right. If I plug 0 in, yeah, that's fairly correct. All right. Yeah. So checking the condition before committing to L'Hopital's is key. Thanks, Howard. So right, you do need 0 over 0. Sometimes if you just try to apply L'Hopital's rule and you don't have the right indeterminate form, you'll get an incorrect answer. All right. So if I just plug 0 into this, it looks like 1 minus cosine of 0 divided by 0 squared. All right. Yep. And remember, cosine of 0 is 1. So this is like 1 minus 1 over 0, or 0 over 0. Okay. So there's like L'Hopital's rule is essentially satisfied here, or the condition to apply L'Hopital's rule is satisfied here. All right. So then we can take the derivative of the top and bottom and try to reevaluate. All right. So what's the derivative of the numerator? Sine x, exactly, right? Because the derivative of cosine is negative sine. So the derivative of cosine is just sine. Okay, and then the derivative of the denominator is 2x. Indeed, it is 0 over 0 again, but that's okay. Essentially, that just means that we can apply L'Hopital's rule again. All right, so you can do this multiple times. So if you take the derivative of the top and bottom now, it'll be the limit as x approaches 0. And right, you'll get the derivative of sine is just cosine. And the derivative of 2x is just 2. Well, you have to make sure that you're still getting an indeterminate form before you plug it in again. If I'd gotten something like 0 over 2 or 2 over 0, I wouldn't want to use L'Hopital's rule necessarily. All right, right. So now when you plug 0 in to this final form, you get cosine of 0 over 2. Cosine of 0 is 1, so this is just 1/2. Okay, I'm going to do B, and then I'm going to have y'all try to look at maybe C and D. All right. So sometimes there's a sort of trick you can use. Sometimes you don't get 0 over 0 or infinity over infinity, but you can rewrite your expression so that you do end up getting one of those um, indeterminate forms. So if I just looking at part B, if I just plug infinity in, like the way it's written now, it's written as a product, 1 over x times ln x. So if I just plug infinity in, it looks like 1 divided by infinity, which is 0. And then ln of infinity, like ln is a monotonically increasing function. So if like the limit as x goes to infinity for ln of x is infinity. Okay, so it looks like 0 times infinity. And this is an indeterminate form as well. I can't really say what 0 times infinity is. All right, but it's not really given to us in a manner we can use L'Hopital's rule. All right, it's not written as a quotient. Okay, we can, in this case, you can rectify it pretty easily by just writing the ln x over x. I already have like 1 over x times ln x, so I can just rewrite this. Okay, Milos is here. Welcome. Okay, so now that we've rewritten it, now if you plug in infinity, this looks like infinity over infinity. Okay, so now we have the sort of indeterminate form that we're looking for. All right, so from this sort of form, we can apply L'Hopital's rule. Okay, and then what is the derivative of ln x? The natural log. Just 1 over x. Great. The derivative of x is just 1, so dividing by 1 doesn't change the form at all. So then what does this limit approach? Yes, it is just 0. So now that I just have 1 over x, if I let the denominator get arbitrarily large, the quotient will approach 0. Okay, so the limit here is just 0. All right, so I'm going to try to get y'all to do C and D. For C, you'll have to do something similar. You'll have to rewrite it because it's written as a product, but we only apply L'Hopital's rule to quotients. All right, so I'm going to try to break y'all into groups again, see if this works any better. 10 groups sounds good. Randomly assigned. Yeah, so LAs, if y'all can like hop between groups and try to answer questions as they appear, that'd be great. I think everyone can still raise their hand too. It erased everything. Sick. Okay, so let's look at these couple problems. So the first one, um, x ln x, is written as a product, right? And if we let x go to 0, the term that's x just goes to 0, and ln of x goes to negative infinity. Okay, so this is an indeterminate form, right? But it's not the type that we're looking for where we can apply L'Hopital's rule. So there's a sort of trick here where you can sort of move one of the terms into the denominator, right? And I'm going to do that with x. Okay, the idea is that x is the same thing as 1 divided by 1 over x, as long as x isn't 0. Since we're letting x approach 0, that's fine. Okay, like these two expressions are equivalent. All right. So I can put the x in the denominator as 1 over x, and then I'll have a quotient where I can use L'Hopital's rule. So this will become the limit as x approaches 0 from the right of ln x over 1 over x. All right. Now if I'm looking at each of these terms individually, ln x and 1 over x, they both approach some kind of infinity. As I approach 0 from the right, ln of x goes to negative infinity, and the term 1 over x goes to positive infinity. So that's fine. They both go to an infinity. The fact that the signs are different doesn't really matter. This is still an indeterminate form, negative infinity over infinity, where we can use L'Hopital's rule. Okay, so as we saw before, the derivative, so now we'll take the derivative of the top and bottom individually. As we saw before, the derivative of ln x is 1 over x. What is the derivative of 1 over x? So on the bottom, negative 1 over x squared, exactly. Okay, so if I divide a fraction by a fraction, you just multiply by the reciprocal. So this expression is 1 over x times x squared over negative 1, which just gives me negative x. Okay, so this becomes the limit as x goes to 0 of negative x. Yep, so the answer is just 0, right? Okay, good. So that's sort of a trick that you have to use sometimes in order to apply L'Hopital's rule. When you have a product and you get something like 0 times infinity, then you can move one of the terms to the denominator generally. All right, so the next one we looked at was part D, which was the limit as x approaches 0 of e to the x minus 1 over x squared plus 3x. The answer for B was 0 as well. Yep. Okay, so for Part D, if you plug in 0, you'll get, so I'm going to see how typing works for this. Since I'm out of room, kind of, you'll get e to the 0 minus 1 divided by 0 plus 0, and this ends up looking like 0 over 0. Right? Because e to the 0 is just 1. So the numerator becomes 0 as well. So we can use L'Hopital's rule. Okay, and then what is the derivative of the numerator? E to the x minus 1. Just e to the x, great. And then what's the derivative of the denominator? Muy bien, muy bien. 2x plus 3. So this is our what L'Hopital's rule tells us, that it's equivalent to taking the derivative of e to the x over 2x plus 3. And now I can just plug in 0. Okay, so this will just give me e to the 0th power divided by 2 times 0 plus 3, which is just 1/3. Okay, great. Let's see. F, the last one, would work out basically the same way. You'd get 0 over 0. And then once you take the derivative of 2x, you just have 2 on the bottom. So now there's no denominator at all. So that one works out pretty easily. E is a case where this is sort of a trick. If I let x go to 0, this looks like 0 over 2. So this is not the type of indeterminate form. This is not really an indeterminate form. It's not something that we would use L'Hopital's rule for. Okay, because we didn't get 0 over 0 or infinity over infinity, and we can't really rewrite it in such a way that we would. Okay, so in this case, I think you actually get the same answer even if you use L'Hopital's rule, but that's basically just an accident. On the discussion from yesterday, there was an example where if you use L'Hopital's rule, you got an incorrect answer. So you would have to do this basically just by dividing by x. Yeah, I think it should go to 0 because x squared will get smaller faster than x plus 2. So you could still like divide out by x essentially. Oh yeah, sorry. I'm actually just being dumb. So 0 over 2 is just 0 by itself. You don't have to really do any extra work. You actually already have the answer. Thanks, Howard. Yeah. Okay, all right, so that's all for today, I think. Thanks for showing up. And I'll see y'all on Friday. I will have office hours after this in the main room. So there's like a main class where I'll have office hours. All right, so I'll be there in about 10 minutes. All right, thanks, guys.